So today I think it's our second hands-on sessions on LLM. More specifically, like we will use to fine-tune LLM. And the use case I pick is actually recipe generation. So I find it a very interesting topic. So basically, is you provide a list of ingredients as the input, and then ask the LLM to generate a recipe for you to how to turn your ingredients into a delicious dish. So that's the use case for today's kind of play demos. So last time we have like talk about like how can we build a RAG solution with the Llama 3 instruct. Of course, you can replace this LM, although it's kind of like a Llama 3 hands-on, but you can easily replace the model ID with any other Hugging Face model ID so that you can switch to any LM at your choice. And this is the link of notebook last time. So if you are interested into how to build a rack with LLM, you can just click this link and go through the exercise we have last time. So today's session, we will focus on the fine-tuning part, and we will fine-tune it for the recipe generation. So this is still pretty much the same prerequisites as the last time. Hugging Face, I'm not sure right now, but at the time when I try to get access to Llama 3 model, I still need to submit request to get access. Not sure whether it's still the case right now, but if you click on it and if you see that it asks you to, to get the permission to access, you still need to submit the request. And then you may need to wait for quite a few hours for you to get the access. But I don't think that will stop us. You can just easily replace the model ID with any other available Hugging Face models. And then you also, if this is your first time setting up like a Hugging Face, you will also need to create a security token over here and then put the tokens like as the Hugging Face HF underscore tokens over there so that your notebook have the authorization to get access to your Hugging Face repositories. And then you need to download the requirements.txt. So it contains all the dependency libraries that this exercise will depend on. And then you need to download this CSV. So these files are just hosted in my Google Drive that you can easily download it. And this recipe datasets actually comes from the Kaggle datasets. So if you are interested to really get a working recipe generation model and you want to fine-tune this model on a larger GPU, with a bigger memory on a larger dataset, you can use the original datasets, which has, I think, almost a million, like a few 100,000 ingredients to recipe datasets. Okay, and then you need to run this to install your dependencies and then import all the modules over there. So I think you can just do it along, or I can just quickly work through that, and then you will have the time to run and try it out yourself. So the first step is you need to load the LLM. So this part is the same as last part. Like last time when we built the rack, we need to load the LLM. And then connect it with the long chain kind of, and also the Docker vector database to create that rack application. So this process is almost the same as the last time. Well, you need to, so if this is the first time you're using Hugging Face to load, this is the main steps, right? So you need to get the model ID from the Hugging Face website. So you can find all types of models there, from Metas, from Databricks, from Google, all kinds of models hosted over there and at various different size. So this time I still use the 8 billion instruct models from Llama 3. If you don't have access to Llama 3, you can just comment on disable this and then use this Dolly 3 billion model. I think this is like publicly accessible models once you have the Hugging Face account. And then you need to create your token, right? Token is basically turn the text into IDs so that the model can understand. And then you use this because all this LLM is kind of like a causal. Causal means like it can always like predict the next future token based on the historical tokens, right? So this is like a causal language model. And then you can load this Llama 3 model by providing the model ID. Due to the GPU limitation, like free GPU you get, I think is with maximum about like 20 gigabytes. So this is how you can make it work to run on a free GPU that Colab has. So you need to load it into like 8-bit equals 2, and device map is auto then so that it can automatically use the GPU available. Then you can define a pipeline. So the pipeline is also like from the like all kinds of pipelines that can support different kinds of tasks like text generation or image captioning or sentiment analysis. So basically it kind of concatenate all the components together for that specific use case. So it makes things easier for you, right? Instead of you piecing it up together, you can directly use this pipeline function just by providing the token and model so that you can have a pipeline and directly run inference with this pipeline. So that our task is a text generation because our input is a text and our output is also a text, right? So it's kind of like just a text generation task over here. Okay, so that's how you load the model. And then once you load the model, you can just directly prompt the model. So you can just prompt whichever model you are able to load in. And then you will get the text out over here. Like what is a large language model? And then if you run this pipeline, directly passing the prompt to this pipeline, you will get your output. Okay, so that's the model loading. I will pause it here just to see if there's any quick question. Okay, if not, then moving next is the data preparation. So I must say, like for all kinds of model building, usually at least half of the time, 50% of the time is spent on the data preparation because we need to get the data into the right format so that the model can understand and can be trained upon. So we need to load the data in. So usually like when we train the model, we use the datasets package. Like the PyTorch and other deep learning package can easily run epochs with this dataset format from this datasets library. Then you can easily load the CSV over here. Yeah, due to the time, I just select like 100 samples from that because when you have a larger data set, it takes a much longer time to fine tune the LLM. So for demonstration purpose in this notebook, I just select the 100 samples from this. You can also choose to use all over there. And then this is the data looks like. Right, so it has the features. It's kind of like the column names in your CSV, like name, minutes, tags, steps, ingredients, and number of ingredients. And this is the number of rows in the data set. You can also see what is the first row looks like, right? So for example, this is stuffed some shells cooking. This is a steps, right? So step 1, step 2, etc. And this is your ingredient, like a ground beef, yellow onion, tomato paste. And then we need to prepare the template. So the template is the prompt format into the LLM. So I decide the prompt is like this, like generate a recipe using the ingredients provided below. And then I start with the title and then list the recipe in steps. Right, so basically the format is like you pass in the ingredients here, the response, and then the response should be with the title first and then the steps. And then I need to format that CSV into the prompts that I just set up. So we can write just like as a processing function, and then we pass the using the dot format function to pass the ingredients from the CSV, pass the title and the recipe from the CSV into the text segment, like for the prompt. And then the final training is basically a concatenation of the prompt and the answer. This is our training data set that includes the prompt and the final answers created from the data set. So if you run this, like map this, so basically you will apply these functions to each of the row in the data set, then you will get this, right? So you see it's much larger right now. It adds these additional features like prompt, answer, and text. The text is a concatenation of the prompt and the answer over here. So and actually this part is what we need as the input to train the model. And then we also need to kind of a function to generate the token embeddings. So basically to apply the tokenizers from the Llama 3, right? Like in the beginning, we are able to not just get the model, but also load the tokenizer for the corresponding LLM. Each LLM has its own tokenizer that the word has a different ID assigned, so that which can be understood only by that LLM. So we need to make sure that we use the correct tokenizer, or else LLM do not understand at all what it means. So over here we apply this preprocess function so that all the text in the datasets is tokenized into the IDs. Yeah, so this is just doing some filters to make sure that it's smaller than the max length, which I set it to a really big max length over here. I think the recipe in this data set, it should be just around 1,000 tokens. And then you can do the train test split. Like 90 goes to the training data sets and 10 goes to the test or the validation data set. Okay, so that's the data preparation. So overall, is you need to use the data set object to load the CSV. You need to format the transform it into the prompts that you desire for the LLM, right? And then the last is you need to tokenize it. So that's the major 3 steps of how you prepare the data. Okay, any questions on the datasets part?
Can I ask a question, Jan, on the train test split? So this is more like traditional, ML training. And I imagine you'll have 90 recipes and their steps for 90 ingredient recipe combos, and then 10 recipe ingredient combos for test. What if in the test you have some ingredients that you've never seen in the training set? What will happen in that case?
It's okay. That's the power of LLM, right? The LLM should have seen all the tokens already from the pre-training phase. So the LLM, even without fine-tuning, the LLM should be able to generate some outputs already. The fine-tuning part is more like adapt the LLM to understand the prompt, the instruction, and the output formats to tweak the LLM so that it outputs the way that you want it to generate. So that's the purpose of the fine-tuning of LLM. LLM has already seen all the tokens already, so we do not need to worry about whether that token is seen or not.
You're relying on the pre-training part on the foundation model of this LLM, that it has been exposed to recipes.
That has been exposed to everything on the internet.
Yeah. What if the use case was different and you had a specific use case that
I see. Yeah, if it's like not present in the pre-trained data sets, then you need to pre-train. Like you need to use the master language kind of pre-training or next token kind of prediction pre-training to kind of pre-train the LLM so that it's already familiar with the tokens in your data sets.
You need to continue training the entire model, not just fine-tune it.
Yeah, not just fine tuning. If you have a very special data sets, yes.
Got it. Okay, that makes sense. Thank you.
Yeah, the recipe one is like a very general because it's very yeah. Question?
I have a question on the embeddings. Is that embeddings required only for RAG, or is that being required to send an input to the LLM model?
Embeddings, there's no, this is not the, I would say it's not embedding. This is to generate token IDs, I think.
Oh, those are not embeddings?
Yeah.
Okay.
Tokenizer, yeah.
Okay, it just tokenize and send the input.
Yeah, send the
LLM.
list of integers to the LLM.
So we are not using any vector database here for embedding.
Yeah, no vector database here.
Okay, thank you.
Yeah. Question: before we perform the training, do we worry about some of the data might not be clean, or some of the data row might have some like missing value? Do we worry about that, or do we need to do something?
We need to do something. I mean, it's in a real, in a real case of if you really want to fine tune LLM for the best performance, you need to do all kinds of the previous like data engineering, feature engineering stuff. You do like do a exploration analysis of the data sets to see, okay, what's the like what are the unique values, what values make sense, what are the missing ones, what are the imputations to the table, etc. to get the best performance. Because if you give bad demonstration, there it will hurt the performance. Maybe it will even worse than the pre-trained model.
Yeah, I know, like for this case, for these test cases, we only have 100 row of data, but in the actual scenario, maybe we have like thousands of, millions of loans, or not loan, millions of the records. Do we really need to clean up the data, because that task could be substantial, right?
No, I mean, cleaning is more like formatting. So even here, I have do some cleaning. For example, this like 1, 2, like it's kept as separate, and I want to clean it because, so you see, like if it's larger than 1, then I will concatenate it over there, because some lines do not have 1, 2, 3, and some rows the steps has 1, 2, 3. But I want to make it consistent, so I decide to remove all the numbers and just list them using a new line tag to just by placing the new line tag like this to distinguish like a different step instead of putting the 1, 2, 3, so that I need to filter out all the characters that I can automatically filter out myself, so that I can make sure that the format is consistent. I do not mean that we need to check all the recipe to make sure that the sentence are correct or it makes sense. That yeah, it's too much. It's more like we want to make sure the data formats are consistent as the input.
Got you. Thanks.
Great questions. Any more? Okay, moving next onto the fine-tuning phase. So we will use LoRA. I think you may have already heard about it. Because like fine-tuning the original, even like 8 billion, like 8 billion actually is not huge, like comparing to 150 or even more, over 200 like billion parameters models, right? But even fine-tuning like the all matrices in the 8 billion, you still require a huge GPU with large memories. While the free, you see the GPU RAM, like a free RAM we get on the Colab is about 20 gigabytes, and you see like I kind of tweak the parameter to make sure that I'm almost getting to 100% of the RAM and do not get the out of the memory error over there. Yeah, so the trick here is there's a very good paper. I think this paper is published from Microsoft. is saying that the matrices is all matrices are low rank representations. So instead of these full matrices, like as you know, like the transformer has like the key matrices, right? The matrices for the keys, for the values, for the queries, right? So all those transformation matrices, instead of training like the full parameters over here, you can just decompose it into a latent dimension like R, right? And then you just use like two smaller matrices, and then yet you can recover the original full matrices. So that's the main idea, right? So that instead of to fine tune every element in the full matrices, we can just worry about the two smaller matrices for the model fine tuning. And in this paper, they have also shown that doing this, it actually does not hurt the performance that much, which means that using a smaller computing resources with the GPU with smaller memory, we are able to fine tune the LLM with maybe slightly worse, but a comparable performance of if you just have the full resources to fine tune the original model. So that's a key idea. And they only train like a smaller matrices of A and B over there. And it's very easy to guess. So basically, they have implemented this algorithm into the PAFT package. I think this is performance efficient fine tuning, package. It has like a different ways for you to how to fine tune LLM efficiently, including this LoRA, and also including, I think the other trick is adding adapters to the LLM, right? So it actually has many different options for you to efficiently fine tune. So in this one, we will mainly focus on LoRA. In the LoRA, this is the key configurations over here. So one is the dimension, right? So the latent dimension that you want to compress your original matrix. And then there's like an alpha. So this alpha, I look into the original paper and it says that it will scale the delta matrices, which is the matrix of B and A, like a matrix multiplication. And you got your delta. So this is your delta weights. And then delta weights plus the original weights, you got your new weights. So that's the idea in the LoRA. So it will apply a scaling factors to the delta weight. So they scale this delta matrix by alpha. So it's I think it's kind of some people say like this scaling have a similar effects with the learning rate. To me, it's more like how you want to combine the original weights versus the new delta weights, right? If you want to increase alpha, means that you want to make more impact. You want more contribution from your fine-tuned weights rather than from your original weights. But if you set a small alpha, it means that your modification is smaller, relatively smaller. That's how I understand it. So that you can choose how much impact you want to do. So it has to be a multiplier of R. So it's like 2 times, 3 times, and I set it to 4 times here. So I still want some changes on the original weights. And you can put the alpha over here, like LoRA alpha. Dropout is optional. So here is like a 5% of like activate or deactivate to deactivate the neurons. And I think more special is this, the target module. So you can choose what are the target matrices you want to apply the LoRA on, right? In the Llama 3, I can choose the Q projection. You need to check what are the module names in the architecture. So for Llama 3, it's the Q query matrices and the value matrices. And if you use the Dolly 3 billion model, it's the query key value modules. Basically, you can select what matrices you want to apply this LoRA low rank representation training. So that's your LoRA config. And also due to I want to save the GPU memories, so we can prepare it for 8-int integer model for the training. So you can just call this simple function. And then you can pass in the LoRA configuration and apply this LoRA configuration to the Llama 3 model. And then you can print how many trainable parameters right now in the Llama 3 models. So you see, like originally it's like 8 billion, right? It's like 8 billion parameters. Right now the trainable parameters, because you have applied the LoRA, is 3 million. It's only 4% or less. Yeah, this is 0.04% of the original parameters over there. So you significantly, like, greatly reduce the parameters that can be fine-tuned for your case, so that you can load it in this GPU.
Question, like, how does the 3 million parameter calculated? Where does this come from?
It's from this.
I mean, this 3 million is like the based on.
Yeah, is from A and B. The parameters are from A and B, right? So only fine-tunable parameters in the LoRA configuration is A and B. The original matrices will be fixed, won't get any fine-tuned. The only is these two smaller matrices that you want to apply the deltas, right, to the original. So the fine-tuned ways is these smaller matrices of A and B with the latent dimension of R.
Is it like the print? I mean, is A and B is not the original data. A and B is more like your intermediate level of the transform data, and that data has 3 million parameters.
Yes. It's additional parameters on top of original parameters. Original parameters actually are frozen. There is no changes. The only change are these smaller matrices that if you multiply these matrices together, you can get your big matrices, and then you apply these deltas as modifications to the original weights over there.
So is your 3 million controlled by your alpha and R setting?
No, it's controlled by R. It's mainly controlled by R. So this 3 million is mainly controlled by R and target modules.
Okay, yeah.
Alpha is just a scaling. It doesn't affect how many parameters. So basically, the smaller the R, the smaller the target modules, or you select fewer modules to fine tune, the fewer the parameters. Yeah.
So right now, if I see like you have a Q and V, but if you only have Q, does that mean you will reduce that 3 million to 1.5 million?
Half. Yes, you can try that.
Okay, thanks.
Yeah, it should reduce it by half if you remove the V there. Usually they come in pairs. There.
Can I ask a clarification question? So in cell 14, you're doing your KB training for 8 integer model for training. You're storing that under model, but then you're not using model, you're using this Llama 3. So how is model used and how is Llama 3 variable used here in this cell?
Yeah, it's a good catch. There should be a Llama 3. It's a good catch.
Right?
Yes, it should be.
Or maybe you need model in the second, yeah.
Yeah.
Something.
Yeah.
Okay, yeah. Thank you.
Yep. Any other questions? Yeah, thank you for all the questions and feedback. It's very helpful.
Is the Llama 3 the only thing we can train here, or is besides Llama 3, is there some other thing you can change that to?
You can change it to many other options. All kinds of options. As I mentioned, I put a line over here, right? You can change it to other 3 billion, like even smaller model. You can run if you don't have access to the Llama model. It may take a while if it's the first time set up on Hugging Face, but this one should be, you should get it right away.
Thank you.
Yeah. Any other question? Oh, by the way, if you use the 3 billion model, you need to change the target module names because somehow like a different LLM have a different module names. They do not stick with the same format. So if you choose the 3 billion, you need to change your target modules to like Q key values. Like it's kind of like a Qs and keys. It's kind of equivalent to this in Llama 3. So you need to change the target modules to this for 3 billion.
Could you do also, so QV, could you also do the keys here? All 3 matrices, or?
You can, but I think you will get out of memory.
Oh, you think? Okay.
Unless you have a, actually I already have like the kind of more advanced version, like Colab Pro. Then you can get like access to A100, which gives you I think 40 gigabytes memory, and then I think you can add more modules.
Well, you need some kind of valuation metric in the end to see how it performs by running different tables.
Okay. Yes.
Your dropout rate is 5%. Does that mean you keep 5% or you keep 95%?
Dropout rate is 5%. It should be like dropout 5%.
So you keep 95% of the original data.
Yes.
I see. Okay.
Most of the time, people don't do this. It's just 0%. Actually, I do not observe a big difference. But people say, but I think it may vary case by case. Especially if you have, I don't know, depending on the data. People are doing this mainly for prevent overfitting, as they think. It's like dropouts is kind of like of normalization. So yeah, depending on whether your model overfits, but over here, I think it hardly overfits. So I don't feel like this will have any impact there. You can just set it as 0 also.
Thank you.
Cool. Any other question? And then the next is you need to kind of batch the data sets to make sure that I think you already see this. So this is also an argument you need to parsing into the transformer train function you will see later about like how you want to process a data set, like this data connector for language modeling. You need to pass in the tokenizers and like how you want to prepare the data into batch over here. So I think you should be able to see the, like you can open in tab to see what exactly this function is doing. Like pad it to the maximum length of a batch if they are not the same length. And the next is you need to define your training arguments. To me, the most impactful is the epochs and this, like per device train batch size. This is so it's mainly for training. It's mainly these two. It's very interesting. Like I find it very effective. Because of the limitation of GPU, we cannot run large batch size. So actually, it's a very clever way. So you can do micro batch, and then you can accumulate the gradients across the micro batch to the actual batch you want to get. So in this setting over here, I set the batch size as 16. If I directly do batch size of 16 on this GPU is not enough, like it's out of memory. But what I can do is I can do smaller batch first. Like I can do, you see the limitation of these GPUs, like I can do a batch of 2. And then basically it means that I need to do this smaller batch kind of 8 times, right? 8 times to accumulate the gradients so that I can still support the batch size of 16. So that's the idea. So I really like this configuration so that it allows me to run on a smaller GPU like you can, even if your GPU is smaller, you can just decrease your micro batch size to 1. The effect of this is the smaller the micro batch size, the smaller GPU memory it will require. And also it will takes longer to run, right? But because every time the parallelization is small. If you set it to 1, it means no parallelization at all. You just process the sample one by one over there. So for this GPU, I find like 2 is the maximum we can set, and still I can set the batch size to be 16. That I want to get all the 16 gradients, and I want to accumulate them together to do like 1 backpropagation. So my batch size is still 16, even though the macro one is 2. So that's a trick of how you can save your GPU memory. The other ones I think is pretty straightforward, like the learning rate, the learning scheduler, like linear cosine. I think you can explore like the different options here, and also optimization. What type of optimization? You can also have many different options over there. And then finally we can train. So we need to pass in the model, pass in the tokenizer, all the training arguments, also the training and evaluation data sets, and the data collector. So that data collector is the regional data collector, whether I need to pad my training samples into the equalness of tokens. And then you can kick off the training using this trainer.train. And then you will start the training. To save time, because you see this, I run like almost 20 minutes, just run 2 epochs. Yeah. So, but with a larger GPU, it should be faster. But with this GPU, I would just recommend, yeah, I just change the epochs to 1, so you can finish it in 10 minutes. If you run 2 epochs, it will run in 20 minutes. So that's pretty much the time it takes to run. So, which means that if you have a larger data set to fine tune, and if you want to speed it up, it's better to have a GPU with a larger memory so that you can increase the micro batch size, so that it runs faster on your GPU.
Yeah, can I ask a question on your training set size? Is it 1,000?
No, it should be just 90. It should be just because I specifically select 100. Yes.
Okay, so you just went through them twice.
Yeah, just went through them twice.
It took 20 minutes for both epochs.
Yeah, and this is only updating 3.5 million parameters. Yes.
Okay.
Yes. It is slower than what I thought. So I know there's ways, because like you can use other clusters of GPUs. So now you can imagine like why this, especially Meta, right? Like since they are building these Llama models, they are using, I don't know, like thousands of GPUs and trained for months to get this final pre-trained model. Yeah, it's slow.
The other thing is, I can try it later, but with Colab you get the TPUs. I wonder what is the difference between CPU and TPU.
Yeah, if you tried it out, and yeah, if you have any learnings, feel free to share in the comment. I'd love to see that as well.
Sounds good.
Yeah, not sure whether you need to tweak the, but I think this will apply to all the device. I think it should cover the TPU as well, because if you look at the training arguments description, they have like per GPU, per CPU, and per all the other devices that I am not aware. I don't know what those devices is, but it seems that it does support varieties of device to support these functions.
Okay.
Yeah. So that's the training loss, validation loss, and it should keep improving, because it's not even near the overfitting yet. But yeah, I would recommend, like if you really want to play with it, I would recommend to play with the different device, different configurations, like also the LoRA settings, and maybe write more epochs if you want to further improve the fine-tuning performance on that. And I still get all kinds of user warning. I haven't got the time to fix the user warning. It seems there's some way to optimize. Maybe it's some ways to optimize the speed. It's also worth looking into to see if there's any ways to further like optimize the speed of the training. And then you can save your model. Like you can either just choose to save the 3 million parameters, like instead of all the original ones, just save the pre-trained model, or you can just save the full model with the 3 billion, or just save the configurations of the models. And so that's the model training, and the last is the inference. I think it's again the same process as how you run how you set up the pipeline with the original Llama 3, where you can run the inference. You can still use the pipeline, and it's still a text generation task. You can pass the trainer.model. That's how you get your fine-tuned model over here. Yeah, and then pass all the. This is mostly optional, but sometimes if you don't pass it, you will get a warning. So you still specify the path tokens. And also this, I think it may be, I do not notice any difference, but I think it's recommended in every examples I have seen. This is do sample is just like because it's a generation, right? So every time it's like just a sample, a token from the scores, predicted scores. So it's kind of like a sampling, always like a sample the next word. It's not like a kind of a very greedy, always choose the token with the kind of the best, highest scores over there. So this allows some randomness explorations in your generation. And then this is how you run. You just pass. Again, you need to format your prompt. You can just use the same prompt because this is a prompt that you format your training data sets to fine-tune the model. So you can just use the same prompt as the input, and you can pass in the gradients over here. And it will run also a few minutes, which is again slower than what I thought. So if there's any idea of how to speed it up, maybe it's a GPU I use, or maybe there's other ways to speed up the inference. I know Llama 3 is already optimized because I think they use a grouped query embeddings to speed up the inference, but it's still not as fast as like the ChatGPT. You can just almost simultaneously get the response. I think this still needs the more optimizations here so that you can get a better inference time on this.
Hey,
and
yeah, why do you think the inference here is much slower than the notebook that we ran for the last meeting? Why do you think it's such a dramatic difference?
No, I think it's not. So last time, I think you mentioned the first example, right? So it's you just directly query the Llama 3, right?
Right.
Yeah, I don't know like exactly in the inference how they kind of piece it up together. So basically, you need to the 3 million parameters are all here, right? You need to use these parameters, calculate your delta weight matrix, and then modify the regional matrices, and then pass your inputs through the updated matrices. So it's understandable that I think it's slower than the original one, because the original one is you don't have all these additional calculations. You just pass it once through. Maybe there's a way that we can create a model, like just kind of fully merge them together into one matrices there, instead of you need to calculate the deltas to complete your inference. Maybe that's how I think. I don't know, like at backend, do they do it on the fly, or what I get is directly modified, like a weights modified models at backend. But it seems like it's able to save the weights like directly. It seems that they just separate 2 copies. Like one is the original one is just a smaller set of weights. And then at Inference you need to recover that back.
So if I wanted to summarize what you said, you're saying that in the previous case we just had the 8 billion parameter model. Now we have the 8 billion plus the 3.4 million.
Yes.
That's adding a little bit of complexity, I understand. Okay.
Yeah, but I think it will be interesting to see how they do it. Maybe is it like just the first time it's slow? Because sometimes in even with the transformer, like you need to warm it up. You need to warm up, right? Like the first few times is slow, and then it may have some caching in it. You don't need to recalculate the deltas or recalculate the sums. It can do some caching of the weights, and then it will get faster when you query it a few more times.
Okay.
Yeah, but that's something need to dig into of how to optimize the inference of the LoRA fine-tuned model. I think there should be block on this.
I'm puzzled. I'll just. I was late, so my apologies. I'm going to just ask a couple of questions that may have been answered earlier. When we use the when we're using LoRA, I'm assuming it's using a vector database for part of its inference, right?
No, there's no vector database at all.
Oh, okay.
Yeah, no vector. It's totally different from the first one. So the first session is vector database, no fine tuning. This one is only fine tuning, no vector database.
I see. Okay, different strategy.
Yes, different. Kind of like a different use case. I think yeah, you can also maybe have a vector database of all the historical kind of the recipes, but I see the fine-tuning additional powers from fine-tuning is you can create something new, right? Because if it's RAG, that information has to exist in your vector database so that it can get queried and then provided as context so that you can get the right answer. But for fine-tuning, it's more like to train the LLM to understand the data sets better, to understand how it can put up the answer better. And it's leveraging the LLM, like kind of improving the LLM reasonings in the data sets you provided. And so that it can scale to the new use cases, like even some ingredients or recipes that has never existed in your database, it can still create that. I think that's the power of fine-tuning. Yeah, especially it's a new skill set. It needs to be fine-tuned. But for example, text generation can apply everywhere. Maybe you do not need to fine-tune. Maybe the fine-tune can still help to give you some gains, especially if the tokens are new, domain knowledge is very new. The tokens are the LLM do not understand the text tokens that much from the pre-trained data sets. Then fine-tuning may give a bigger gain there. But if it's a new skill set, right, to understand images, to understand math, to understand chemistry or scientific subjects or coding, then the fine-tuning is a must. Or else I don't think the RAG can solve how LLM can understand, like generate efficient codes just by using RAG over there. Unless you build a kind of a really, really huge database of all kind of coding variations that the answer already exists somewhere, and then the LLM can refer to that to just retrieve the code segment, coding example for you. That is the only way, but it's not a generation.
Oh, that's an interesting point. I'm trying to find a good use case. And how about this? What about doing math? So math, solving mathematical problems doesn't seem like it fits well with RAG, but LoRA perhaps it does.
Yeah, LoRA it does. Yeah, math, I do not feel like there's any possibility with rec.
Interesting.
I'm curious about the output here. So can we see in the output run, and can we talk a little bit about evaluation? There's some chat there in the chat about evaluation. So
yeah, the evaluation
let's talk about
I
the
think
response. What is the response for this simple prompt that you entered?
I think it starts. Oh yeah, I haven't touched base the binary response. So yeah, I think the format is almost what I wish it to have, right? So it will provide a title first. That's all the training examples I put, and then I put steps. I actually in the training example I just say steps and this, but it somehow gives this like steps to make the dish as follows, and then like these steps, and then it has some like a noise output. Every time I run it, it gives me a different outputs at below. Sometimes it cut off at the right timing. Sometimes it will repeating the recipe again at the bottom below. I think that's a issue with the Llama 3. Like it's sometimes repeating itself over here. Like it's repeating again.